basic differentiation.
Yeah. So you just keep doing research, differentiation. Whenever you encounter that function, you just bear in mind, and you can invoke the chain rule.
Mm-hmm.
Does that make sense?
Mm-hmm.
So, for example, yes, I take example. So this is the shortest. So normally function is solved, right? So in general, we just say y equal to say 5x squared minus 7x degree. So we know this is a function. We know that y is a function of x, right?
Yeah.
Okay. Now this is a formula form. So this function. So y is a function. We call it a function. And this function is explicit, right? This is called explicit function. So this is formula. So this is we know x is dependent on x, but this is explicit. You can see the formula. So this is a formula of the function.
Mm-hmm.
But sometimes we know that y depends on x or y is a function, but y is different. Y is, can you see? Here's a square root y, or here's something simpler. This is similar to the inverse function, similar to that.
Mm-hmm.
So if you have another example, this is one. So sometimes we have no formula. For example, we have x squared plus y squared equal to 5 or 25. Can you see that?
Mm-hmm.
So even so, this is implicit. That's this function is in explicit form. We can hardly see the formula. See, so no formula, no formula. So we cannot write that formula function on the right hand, left hand side. There's no formula, but the formula is implied. Should I say imply? Imply the formula. Implied formula for y. You see? Is explicit. Explicit, right? Oh, sorry. What I've done. What I've touched disappear. Undo that. Oh, back. Oh, it's good. It disappeared. So explicit. Okay. So that is implicit, explicit. But that I wouldn't say no formula, but the formula is implied in this equation. Okay. For example, if you do want to solve this formula, okay, if you want to solve for y, so what you can do? Can you try how to solve the y, the function, the formula for y from this example?
Square root of 25 minus x squared.
That's right. You got the 25, take x squared and the square root, right? And of course, sometimes I put a positive, negative. So that implies that in this particular case, we have analytical, we have formula. Can you see? So this is the formula. Of course, the formula is analytical. So this is the formula. So that is the formula. That is the formula. Formula for y. Can you see? Oh, we have done that. However, in other case, or in this case, if you ask you to find how to find the first derivative, how to find dy dx. Do you want to try how to find dy dx? Can you just pick up a positive case? Dy dx. Can we just focus on positive value? Just positive. Do you want to try to work out the first derivative from the formula we have? you have to
Uh,
which rule shall we apply in this case?
over 2.
Yeah, that's right. You can rewrite that in the index form. Oh, integration, not integration.
Oh,
Are you going to do explicit integration or differentiation? You're asking for
yeah.
the differentiation, right?
Mm-hmm.
So we simply found the first derivative in this case. Yeah, that's it.
Mm-hmm.
No, not quite. Can you try again?
I have to use the chain rule.
Yeah, you have to invoke chain rule.
Mm-hmm.
Okay. Multiply the bracket. Yep.
Mm-hmm.
That's right. So in this way, we can differentiate that, right? We can find the first derivative. We can differentiate that. But the question is, can we obtain dy dx without solving for y? You know the question? Do you understand this question? Same example, right?
No, I don't think
You
so.
don't think so? You doubt, right?
Mhm.
And let me show you how to do that. All right. So you use the same example, okay? But this is example 2, same example, but method 2.
Mhm.
Method 2. So what do we do that? We treat that, we know that x and y are variable, okay? So what do? We can just use the differentiation in dx, the first term. We use this term here, can we?
Mhm.
And also we can use the dx y squared, can we? So we differentiate every term. That is what you can do when you start after study calculus. You can do this operation on both sides at the same time. All right.
Yeah.
So of course, for the constant, we know it equal to 0. All right.
Mhm.
So this side is equal to 0. But how about you know how to do that? Can you work out this first?
2x.
Yes, simple. But how about second one? That is a question.
2. Oh.
Yeah, 2y, can you see?
Mhm.
But bear in mind, y is a function. See, y is a function of x, you see?
Mhm.
So therefore, we need to continue. We need to continue to dy dx.
Mhm.
That will equal to 0. Can you follow me?
Yeah.
Because this is similar to the chain rule, isn't it? Similar to the chain rule because y is a function of x, you see? So y is a function of x. So if we want to find we have, so y, in this case, y is a function of something else, you see?
Mhm.
Y is another function. This is called the composite function, do you remember?
Yeah.
Yx, which is a function of another, can you see the u, right?
Mhm.
So therefore, when we actually doing this differentiation, you can, we can, first of all, to call this y squared equal to, can you see? Just for explanation from this part. Can we just let y squared equal to u? Can we? So therefore, the second term, can we just continue? The second term will become, this first term is dx, right? The second term will be du dx. Does that make sense? Equal to 0. If you don't understand this term,
yeah.
and that makes sense now, do you agree? And we also know, and u is a function of y, and y is a function of x. Okay.
Yeah.
That makes sense now. So therefore, whenever you see this term, we have used the chain rule. Okay, we got 2x plus du dy, and dy dx equal to 0. Okay. Okay, can you see this solution now? Can you find the solution now?
2x plus du dx equals 0.
Yes, I just
So then we know
highlight what we are looking for. We are looking for this term. Can you see? We are looking for this term. We got this one. This is by solving, but this time we didn't solve. Can you see? So from either equation, or can we just from some last equation, we just follow this order. You can also get his result from here, but we just try from here. Can you see? Then we just put this on other side. We got we know that du dx is 2y. Can you see? We got we got this put the other side. We got 2y and dy dx were equal to negative 2x. Can you follow me?
Yeah.
And then we can use algebra to solve the unknown. Which is unknown? Which is unknown? This is unknown. You see?
Yeah.
Okay, this is a very short introduction of this explicit differentiation. Can you see? So we solve this first derivative by this simple algebra. 2x divided by 2y, and the 2 canceled. Can you see? So what is y? If you wish to know what is y, oh, we are different by 2. You forgot to write this 2 here. There's another 2 you forgot, half, right? There's 2 here.
Oh,
yeah. Because it's half, right?
Oh, yeah.
Right. So basically you use this formula, so x to the power n, first derivative, right? Equal to n x n minus 1. Did you use this formula, right? So we got the same result. Can you see that? Square root. So of course we don't have to know, but from first solution we know that the y can be written as 2, 5, 25. Or instead of doing that one, I simply stop here because there's no point to solve, because they are not asking you to solve the y. They only ask you to find the first derivative of y, right? So therefore, we can just directly from here rewrite this a little bit. Just then that is just negative x divided by y. You see, which is identical to this result. So that is the method you're asking for today.
Yeah.
Can you follow me?
I kind of don't understand it.
Well, we can try another one. Doesn't matter. We can try another one. So this is basically similar to invoke the chain rule. Can you see? Can we go to another example? If you have textbook, we can use your textbook. But I just imagine one. You see, for example, if I have the sine y, all right, plus this is log x, right? We just imagine some function here, and equal to and x to power 5, all right? So what is can we find the dy dx or first derivative? Do you want to try? Do you want to try? dy dx. Dy dx. Almost, but the first time you are not familiar with this notation, can you see? So basically, this term, you have to be careful. This term, you have to be careful, right? It's not right. Why? Because when you say sine y, can you see? So it's very difficult. Can we just rewrite, can you see? First, we just rewrite the equation. Rewrite equation 1, you see? Before we do some preparation. As u plus log x equal to x squared, where u is equal to sine y. That's it. Can we do the differentiation from equation 2? Yes, we can use this differentiation of Arberton. Not quite, not quite. Can I explain to you again? So if I just show you, so this time can we just write this equation, knowing that u is a function of y and y is a function of x. Can make this? Just specify u is a function of ultimately function of x, but explicitly u is a function of y. Do you agree? So therefore, that is first term. The second term, which I will just copy that one. That is the right-hand side. Is 5. Sorry. Okay. So just imagine we just take this as operator. Can you see? We use this operator to the equation every term. For example, when you in algebra, can you see if you have say 5a equal to b, right? What we can do? We can use the square root on both sides. Can we? Can you see? 5 dx equal to b. We can use the square. Can you see?
Yeah.
Therefore, in this operation, we just or you can multiply. We can use dx on both sides. That is just u, right, plus log x. The right hand side is just d dx. So this is how to use this. How to treat this as operator. So this is we treat this differentiation as operator. It's called differentiation, or it's called operator, mathematical operator.
But how do I get this u then? If u equals sine y, then isn't it just cos y?
Well, you have remember in that case we have invoked the chain rule. Can you see? For example, can we just distribute that 1 by 1? Can you see? We can distribute that. That first term is a du dx, not dy. Can you see? Du dx, not dy. And the second term is d dx, or you know the second term. I just copy that just before we do the operation. And this is just 3x squared. All right, I write down here. Now, this term, we cannot do it. We have to use the chain rule. Do you remember?
Why?
You cannot, because this is a differentiation with respect to the x. But this formula,
no x, yeah.
you can we can only do is a du dy. Do you agree?
Yeah.
From this relation with what's the du dy?
Cos y.
Cos y. Yes, that's right. That's all.
Mm-hmm.
So just treat this as a complex function. So this is a complex function. Complex. Composite, sorry, not complex, composite.
So if
function.
sine y is u, what is y of x?
Oh, well, what does the chain rule say? Can we just recall the chain rule? Okay, the chain rule, which is we used this before. So what does the chain rule say? So if you have y equal to say e to power of x squared, for example, all right?
Mm-hmm.
So we cannot find the first derivative easily, but if we just introduce a u equal to x squared, and then y will equal to e to u, all right?
Mm-hmm.
And also from this one, we got a du dx can be worked out at 2x, you see?
Mm-hmm.
So according to chain rule, the chain rule tell us dy dx, what we're looking for, can be written as dy du, you see, multiply du dx.
Mm-hmm.
You remember this is chain
Yeah.
rule? Yes. So we got everything. We got dy du, can you see?
Mm-hmm.
What is dy du? Dy du is EU, can you see?
Mm-hmm.
We got du dx. So therefore, they just multiply them. 2x multiply EU.
Isn't it EU? Oh wait, no, never mind.
Hmm?
Yeah, no, sorry.
Can you follow me now? Yeah.
Yeah.
So you really have to digest why we invented the chain rule. The chain rule is used to dealing with a composite function. So this is called a composite function. So in other words, implicit function is a function that we don't have the formula yet. Understand? If you see this term in the equation and knowing that particular, say in this case, y is a function, but we don't have, in order to find the first derivative, we don't have to solve for y in the first place. So that is the question. And this question has answered, can you see?
Yeah.
So in other words, you don't have to solve the y first. You can just assume that y could be is a composite function of x.
Yeah.
This time, yeah, good question.
For this question though,
Which one?
since it's sine y,
oh, we haven't solved that yet. Not yet. Yeah, we haven't solved that yet. So in this case,
u equals sine y and y equals y. Wouldn't it just be 1 times not u, which
not
is
y? How do you know y equal to y?
Because there's no like y squared plus x here.
Oh, this is not a square, but this sine function. It is a function. Can you see? It's important
so
to understand.
The u function then?
Well, in this case, do you remember we introduced this u? So can you see? Here, what we have done here, we introduced the u. Can you see, to represent this term, which contain the y. Okay.
But since it's not like sine y squared plus x, wouldn't the derivative of that just be 1?
No. How come? Let's go to the too crowded. Let's start a new page. And if I just rewrite that question, that is we have the sine y, right? Plus log x equal to x cubed. Okay. So with this implied y is a function of x. All right.
Yeah.
So So therefore, the question is how to find the first derivative or how to find the dy dx. That is the question, right? So in this case, there's no formula for y, but we are trying to solve, we are going to obtain the first derivative without solving the formula for y.
Yeah, but what would
Can we just try it again?
u equals sine y?
Yes, okay.
What would du over dx times d?
Oh, you have used a chain rule. That's why you forgot the chain rule. No, I show you. That is what, or dy dx, you can stop here. We don't have to go further. Oh, hang on. Is that y or u? Y? Is
U.
y? Is u? Oh, that's why we have to record the chain rule. I show you, right? This is du dx. Can we just multiply dy divided by dy? Can we?
No.
Oh, sorry. It's the other way around. We not start from du. Yes, okay. So we are looking for du dx, right? Can we, yeah, I just repeat. Can we do that? Can we just multiply dy and dx? Can we, dy? Can we? No, why? dy is equal to 1. Do you agree?
Yeah.
So we multiply y, doesn't change the equation. Did we change the equation at all?
No.
No. So certainly we can. Do you agree? We can do. And the next trick is that can we swap these two? Can you see? Can we swap these two?
No, because then it would still be the same thing. It would still be 1.
Yes, so we can swap that. That became du. That's how the chain rule was introduced. And that is a dy. This is dy, but the denominator became dx. Can you follow me? That is the trick we used. You see, instead of work of this derivative, we can find a product. So because in this one, do you think you can solve the problem now? What is the du dy and what is the dy dx? That's what we are looking for. dy dx is what we are looking for. Do you agree? But do we know dy du? Given this
Cos y?
Yes, that's right. Do you know what I mean? We solved that already. Can you see? Can you write down? Did you say cosine y? Yes.
Yeah.
Yes. Okay. We keep that. Keep this one is what is I'm looking for. So this is something we are looking for. Do you agree? So we substitute that into this formula. You see. So if we introduce, if we just let this happen, the equation. So equation 1 will become u plus log x equal to x cubed, right? Equation 2. And again, can we just apply d dx on both sides? That is a log x. And this is just because you can, that's how you can treat the equation by multiply anything or doing the same mathematical operation. Can you follow me?
Yeah.
And this one, I can distribute this operation. Can you see? So that first term became du dx. The second term became d log x dx. All right, equal to we just work out this one. It's a 3x squared, or du dx equal to 1. I just write down here. Equal to 1 over x equal to 3x squared. You see? We have, in this way, we found the formula for the dy du dx, but we are looking for dy dx. What can we do?
We can do.
Do we know dy? Do we know du dux?
Yeah, cos y.
Yeah.
So that's times.
No, we don't know du dx, do we?
Oh no, we don't.
Well, that is what we just found out. So this is what we know. Can you see? Can you see that? So in other words, we can rewrite the purple term into this product. Yes. All right. We got what we want. Although still you have to solve some simple algebra equation. Can you see?
Is that?
Yep, that's right. That's it. Of course, you can simplify a little bit, but that is the trick we used to get what we want by using chain rule, by treating the term contain the y as a complex function.
Yeah. Okay.
Got it?
I think
you can. Do you have textbook? You can pick up question from textbook. Do you have textbook? Do you have a hard copy or do you have a digital book? Or?
I think I have some digital copies.
Yeah, you can send. You can copy the question on the whiteboard. You can try to solve. You can solve. In front of AD. You can looking for the chapter first, the title of chapter first.
Oh yeah, I found some. I found one.
Okay, you can copy to the whiteboard. Yes, y square. Yeah, this is similar to our question. Yeah.
And then it says find
to find dy dx. Yes, right. Go on. Okay, same type of question. So you are looking for this. So what can we do? We have equation. So we have used this equation. Yeah, yes, that's good. That's right. Yes. That's right. Yep, that's it. That's it.
Yeah. Oh.
Yeah, that's it. Is that quick?
Mhm.
If you solve that one, you take longer time. This is not required, but you can also just write that into as x as a function. We often say we put the we put x. Can we replace this y? So this y is x cubed plus 3x squared. Can you see? It's not required, but you can make it looks better. You can put you can put x. You only use x on the right hand side. All right. So that's your question one. Can you pick up another one? So you don't have to solve the formula for y. This is similar to our first example, right? Yes, that is also.
I lost my question.
Oh, you can make up one. Can I help you to make something there?
Oh, there we go. 6.
Okay. Equal to a constant. Good. Yep. Dy dx. No, be careful. Try it again. Can you try it again? Was something wrong this time? What can you see? You see this is a product. Can you see? So this is a product. No, still the same. You have one term. I just remind you, can you see what you have here that you have 6, can you see? 6xy. You apply the dx dt here. Do you agree? So in this case, in the first place, you have to consider this is a product, 6x and y, right? Or in other words, we have to invoke the product rule. You see? So u equal to 6x, right? and v equal to y, you see. Do you remember the product rule? Yeah, it's just uv dash plus u dash v, you see.
Yeah.
Okay, what is u? U is a 6x, right? What is v? V is a dy dx, okay? dy dx. dy dx, can you see that? And u dash is 6, right? U dash is 6. How about the v? V is y. So be careful. This second term must contain the two part, the sum. You have used the chain rule, you see. So that is a little bit challenging this time. This is chain rule. You have to invoke the chain rule. So this is a chain rule. All right. If you use a chain rule, that will help you. Okay. What we are looking for?
dy dx.
Yes, we are looking for this dy dx. So we solve that, can you see? Dy dx is one, dy dx here, another is here, can you see?
Yeah.
Okay. So you can just treat this as unknown and just use algebra to solve this unknown. That's right. Yep. Can probably divide it two to simplify the number a little bit. Is cofactor 2. That's it. That's it. Okay, good.
Yeah.
Make some progress now. Okay. Yeah, this is challenge. This is more challenging than one we just encountered. We didn't use chain rule, and no, we didn't use a product rule. Okay, I'll try one more question.
Could you come up with a question?
Oh yes. Can we make up one? Let's just say we just basically we provide an equation, right? We have can we just use the log square root y squared take 1 and equal to e to the power of y, and make it more complicated. Can we put the x in front? Okay, can we find the first derivative of dy dx?
Um,
Yes, good. You remember that. Oh, almost. If that in this case, can I show you how to write this one? You just you solve the left hand side first, right?
Mhm.
You can left hand side first. Otherwise, you get very confused. Okay. And then after that, you do the right hand side.
Mhm.
Okay. That would be easier. Right hand side. So you have you have divided that already. You have use this. Can you see? If you do this, it's too many things to write. Can you see? One thing you missing here is you didn't write this dy dx at the end. Okay. Can we just call this right hand side, left hand side? Can we work out the right hand side? So this is left hand side, sorry. Can we work out the right hand side now? We do it one by one.
I think I did the right hand side wrong.
It's a product, isn't it? It's a
Yeah.
product. Do you mean this is the first derivative?
Mhm.
Do you mean, are you doing this first derivative, right? Square root?
Yeah.
Yeah. Okay. That's right. So that is these all belong to the left hand side, right?
Mhm.
Okay. So can write down here. So left hand side is just equal to 1/2 square root 2y multiply dy dx. That's right.
Times this.
Yeah. Times this part. Yeah. Oh, yes. Probably this is not. Oh, yes. I think we should be solved that one. Yes. So the strategy is just work out this. So basically, can we just do it again? So for the left hand side, we are basically looking for dx of this complex composite function, right? Y squared take 1. And the first one is the chain rule. We got this square root y squared take 1. And you use your result, right? Your result is half and half y. No. This is not 2y. No, that's wrong. This is wrong. You see, you have to copy that here. Can we check?
Is it just y because it's half times it?
No, this is you are looking for the we haven't finished this yet. Can you see? You have treated this can we treat this as log u? You see? Is this log u? Then we have to use the chain rule, right? So therefore, in this case, this first part and the chain rule allow us to work out the y squared take 1, negative half. And then we have multiplied 2y. And then we have multiplied dy dx. Can you follow me? So it's not simple. The left-hand side, can you see?
Yeah.
The left-hand side, if you do the first derivative, first is 1 over this function, right? That's right. So we got 2. It's half and half. It's just, you can cancel the root. Can you cancel the root? Because this is also square root, 1 over square root. little bit algebra. Yeah. Yeah, square root is, yeah, you have a product, square root. Yeah, cancel the square root. Yeah, that's it. That is the left-hand side. Wow. Okay, then we can, yeah, can you see the space? We can, one moment, I will find some area. We can use this area to work out the right-hand side. So we can use this area. Yep. Yeah, we can use this area. So right-hand side is the product, can you see? You have used a product rule. Did you use product rule? Yes, that's right. Whenever you encounter the y, if you first found where is the dy dx? You missed out where's the dy dx? Where is the dy dx? We have put it somewhere. Where did you do the first derivative with the second part? Yes. Yes. In that case, you have to put the dy. Can you copy it here? Dy dx. Don't forget y. When you do the first derivative, you have to include this term, right? And how about the second term? Second term is this one.
Yeah, it's just dx.
Yes, ex, right? Ex, okay. Plus ex, okay. Okay, go on. Oh, ey, yeah, be careful, ey, e to power, yeah. All right, which term is unknown?
This one.
Yeah, that's right. You got this dy dx on both sides. Good. Yeah, that's right. That's almost done. You can go further, but the rest is just algebra, okay? Simple. It's Well, good. You know this method now. I
Yeah.
think this is a bit more challenging, right?
Mhm.
But another thing you probably will realize that the question is that the question here we're asking today is that whether we can find the derivative without solving the y. Now it's certain now. Do you agree? But
Yeah.
beyond that, the question is sometimes we cannot solve the y. Do you understand?
Mhm.
Even we cannot solve because sometimes it's impossible to find the formula for y, such as the question we just solved. It's too
Mhm.
complicated, right? If you want to solve the y from this question, too complicated. Can you see that?
Mhm.
Almost impossible. But that doesn't stop us finding the first derivative. So
Yeah.
that is why this method is so versatile, not just avoid solving the formula, but also they can find derivative of function without even there's no analytical formula exist.
Yeah.
You have done quite well. Done quite well.
Yeah.
Well, your
Mhm.
calculus is so good. Whenever in the future you tell your colleagues that I know calculus, right? Very powerful, very powerful. Yes, yes, you are studying this calculus very well.
Mhm.
Okay. Any question?
No, thank you. I learned a lot today.
Well, I will save that and let's see. Talk to you Friday, right?
Mhm.
Okay.
Yeah.
Okay.
Thank you.
You're welcome.
See you on
Goodbye.
Friday.
See you.
Bye.
Bye.